All right, so yesterday we finished up talking about isotopes. We said isotopes differ in the number of neutrons, but an element is always defined by the number of protons. And when you have an element symbol, the lower left-hand number is always the number of protons. Top left-hand number is number of protons plus neutrons. All right, so let's do a little practice, and I'll show you what's pretty standard on my exams. And for this one, I'm going to give you an element. I'm not going to give you the proton number, but how can we determine the proton number? The symbol, right? So use the symbol to your advantage. So I've got this compound, got chlorine here, and specifically this chlorine is going to be 1 minus. That means it has an extra electron. Electrons are negative, so if it has an extra electron, it's going to have an overall negative charge. All right, and then the next one is uranium. And then this last one is one of the nasty radioactive waste products from reactors. This is cesium-137. All right, and I want you to determine the number of protons for each of these, the number of neutrons, the number of electrons, the mass number, and the atomic number. So I'll give you a minute to work on this, but check with your neighbor if you're a little stuck. Let's do this. Let's work through the first one together, and then we'll come back and look at the last three. So the first one, how many protons does hydrogen always have? 1. And we know that because its atomic number is 1. Atomic number always equals number of protons. So again, we can go over here and we can say atomic number equals number of protons, which in this case is 1 for both. All right, what about neutrons? Could be 1, right? So the mass number, you can subtract out the number of protons. That'll leave you with the neutrons left over. So that'd be 1. All right, how many electrons will hydrogen have if it's neutral? Be 1, right? It has to balance out the number of protons. And the mass number? It's number of protons plus neutrons. So we go ahead and plug this in as 2. All right, so let's quickly try to go through these next 3. All right, for the sake of time, let's try to work through some of these together. All right, chlorine. How many protons does chlorine always have? 17. If we look at the periodic table, its atomic number is 17. So I'll plug that in. And like I said, number of protons always equals the atomic number. All right, how many neutrons must it have? Be 35. That's the mass number minus 17. Be 18 neutrons. And like I said, the mass number is always that top left-hand corner, so we can plug that in over here. Number of protons plus number of neutrons. All right, now the tricky one. How many electrons? 18. It's got 1 more electron than proton, which is why it has this negative charge. So in this case, it would have 18 electrons because we added 1 extra, right? All right, uranium-238. How many protons does uranium always have? 92. All right, that's its atomic number, so we'll plug that in. How many neutrons will uranium-238 have? Be 238 minus 92, should be 146. How many electrons? 92, assuming that it's neutral, right? No extra electrons, no electrons being stolen. And its mass number is going to be 238. All right, last but not least, the nasty one, cesium-137. Cesium on the periodic table is atomic number 55. So I can plug that in here. That means that it must have 55 protons. How many neutrons? 82. So we do 137 minus 55 gives you 82. If it's neutral, the number of protons must equal the number of electrons. So it'd be 55, and then the mass number would be 137. All right, let's do a little thought experiment. Okay, and in this experiment, I'm going to say, all right, we've got some sort of element. We don't know what this symbol is. I want you to help me find that symbol. And then we're going to imagine what happens if you add in a proton. What does it become? And then down here, we can imagine, what if we removed a proton? What would that become? So this is adding a proton, going horizontal, removing a proton, going down. First one should be pretty easy, right? What goes in this first box in the top left-hand corner? What symbol? Which one? CR, that's chromium. So we would say, all right, this must be chromium, and we know that because the atomic number is listed, it must be 24, right? All right, what happens if we add a proton? Does it become a new isotope? No, it would become a new element. Specifically, which element? We'd go up one, right? So it would go up to 25, which is Mn. All right, so that's manganese. If we think about what goes in this lower spot, what does that lower number become now? Be 25. We went up one atomic number because we gained a proton. What about the mass number in the top left? We gained a proton, so it must go up one as well. So we'd say 53. All right, and then last but not least, do you think this will contain a charge? Yeah, definitely. We added a proton. A proton has a positive charge. So this should be 1 plus, right? That indicates that we gained some sort of positive charge in there. So we do want to indicate that. All right, let's do the next one now. What happens with chromium if you remove a proton? Must go down in atomic number, so it becomes V or vanadium. All right, atomic number must also drop, so it'd be 23. Mass number would also drop by 1, so it'd be 51. And now what would the charge be? It'd be -1, or 1 minus. All right, last but not least, we can imagine what happens if we add a neutron to this. All right, is it going to still be chromium? Yeah, definitely. So it's still going to be chromium, still going to be atomic number 24, but its mass number is going to go up to 53. Will it have a charge? No, because neutrons don't have a charge. All right, so sometimes I do these on exams just to make sure that you understand what each of the subatomic particles does. All right, so let's go ahead and look at symbolic representations of atoms. Sometimes I like drawing out what's going on. And hopefully the internet will work. I've got a good video here. I'm a dog fan, and these dogs do a good job of explaining what's going on. Do you want to flip the lights? Do you mind flipping the lights over there?
Yep. Welcome to Dogs Teaching Chemistry. Our second lesson is on the atom. All substances are made up of matter, and the fundamental unit of matter is the atom. Atoms are made of 3 smaller things: protons, neutrons, and electrons. Paige and Dexter are going to help build an atom. Protons are positively charged particles. Neutrons have no charge and are neutral. Protons and neutrons are located in the center, or nucleus, of the atom. Electrons move around the outside of the nucleus and are negatively charged. Electrons move about so fast that they form clouds that surround the nucleus of the atom. Let's try to figure out what element Paige and Dexter have made. Dexter is counting how many protons we have. That'll give us our atomic number. Looking at the periodic table, you can find the atomic number, which is usually located in the upper left corner of an element square. The atomic weight is the number located on the bottom, which is the number of protons and neutrons in an atom. Great job, guys! The element is helium. Thanks for watching.
I don't know why, that video makes me really happy though. Alright, anyways, moving on. Let's practice drawing out what some of these look like using pictorial representations. So we're going to draw lithium-6, and the symbol for lithium looks like that. And I'll kind of color code things. We'll use black dots to represent neutrons. I'll use red squares for protons, and blue stars for electrons. All right, if we think about lithium-6, how many protons must it have? Not 6. If we look at the periodic table, lithium's atomic number is 3, therefore it has 3 protons, right? Okay, so I'll put some protons in here as red squares, and we've got 3 of them. So that looks good to me. How many neutrons must lithium have, or lithium-6 specifically? 3, right? So it's mass number minus atomic number. So I'll go ahead and draw 3 of these. And if we think about this space in the center of the atom that contains our protons and neutrons, what's this referred to as? Nucleus. And then you have this big cloud going around it. This is where the electrons are. All right, how many electrons must we have? 3. It must bounce out the protons, assuming there's no charge. So I'll just draw 1, 2, 3 like that. So sometimes it is helpful to draw these using a pictorial representation. Let's try a little bit harder one. Let's do lithium 7, 1 plus. Same idea though, how many protons will this one have? Still going to have 3. By definition, lithium will always have 3. How many neutrons? 4. So 7 minus 3 is 4. So I'll go 1, 2, 3, 4. We've got these in that nucleus that we were describing. And now how many electrons will this lithium have? 2, right? In this case, it has a +1 charge, which means we must have removed a negative charge, in this case, an electron. So I'll go, all right, 1, 2, and it's in that cloud. Like I said, this green circle here is my nucleus. There may be a question on our first exam where I ask you to try to represent a given atom or isotope. All right, so I emailed everybody last night about skipping question 3 on the pod, having to do with valence electrons. So let's briefly talk about what those are. And let's go back to that lithium-6 example. We said lithium had 3 protons, 3 neutrons. I'm not going to do the shapes. However, the electrons actually occupy slightly different space. So I'll draw these out. Actually, let me do it like this. So you've got two electrons that are closer into the center, meaning closer to the nucleus. They're typically thought of as being lower in energy. The third electron is going to be out further away, and we call these outer shell electrons. Also known as valence electrons. These tend to be reactive. The two that are closer to the nucleus are called inner shell electrons. And they are not very reactive. All right, so when we think about a chemical reaction, typically it's involving the valence electrons, not anything else. All right, it does get a little bit confusing, so I want to explain what's going on. The key thing to remember is that electrons occupy a 3D space called an orbital. It isn't my favorite term because orbital implies orbit, right? These don't really orbit like a planet does. It's more just this random probability map. So let's make a note of that. It's not like 8 planets orbit. It is a probability map. So it basically says in this three-dimensional space, there's a high probability of finding your given electron. So we'll talk about this in a little bit of detail. So let's do the shapes and types of orbitals. All right, the first and most basic one is called an s orbital, and it's a sphere. And it's sphere shape. Pretty easy to remember, but it basically says in this sphere cloud, you're likely to run into some of your electrons. All right, there's more complicated ones though, and in order to show these more complicated ones, I'm going to show Cartesian coordinates. So I'll do this 3 times to show all of the new orbitals that we're referring to. Okay, the first one has this spot in the center called a node, and then a lobe going up like this and down like that. This is called a p orbital. And people describe this as a dumbbell. So you have one going straight up and down. You have another one going left to right, like that. And then you have another one going kind of in and out like that. These are all considered p orbitals. The main thing to remember with these orbitals is they show the likelihood of finding an electron in that 3D space. Yep.
What is up relative to here?
What's that?
Well, like in your XYZ here, what is up relative to?
It's just saying you've got 3 different orientations of p orbitals that are all different from one another. They're kind of offset by 90 degrees, if that makes sense. So all 3 of these orbitals exist on a given atom.
Oh.
And then the s orbital, this same red dot, meaning the center of the atom, would just be smack dab, and they kind of overlap over one another. But it's interesting, with each of these orbitals, you can shove in 2 electrons into this orbital. You can shove in 2 electrons into the p orbital going straight up and down. You can shove in 2 electrons to the p orbital going left and right. and then an additional 2 electrons to the ones going back and forth. So how many electrons for all the p orbitals? So just p orbitals? I'd say 6, right? So you can fit in 2 in this one, 2 in the next one, 2 in the last one. So p orbitals are a bit different that way. So let's make some notes about this. So each orbital can only hold 2 electrons. That's the first point. And then once an orbital is filled with 2 electrons, you must go to the next orbital. That is higher in energy. All right, so I'll kind of show you what's going on in a super simplistic term. This is called quantum theory. And the quantum model says essentially there's discrete energy levels that electrons can occupy. And to show this, I like showing it as a stair step. So for example, this first stair step, we can fit 2 electrons. And then when we run out of spot on that step, we have to go up 1 step. It seems kind of intuitive, but they didn't know that for a long time. The key takeaway is that electrons can't be halfway up a step. That is to say, they occupy an orbital of specific energy. It's not this continuum where you could be halfway in between energy levels. All right, my next question is, which of these electrons is going to be valence electrons? The ones higher, right? So the ones higher basically have higher potential energy, right? So valence electrons occupy the highest energy orbitals. So that's a really simplistic view of the quantum model. People get really overwhelmed when they hear the word quantum because it sounds fancy. Basically, it's just saying there's discrete energy levels. That's all it is. All right. So now I'll show you a simple trick for determining number of valence electrons. So how to determine number of valence electrons. These are the ones we care about. Like I said, the inner shell or core electrons aren't really reactive. And if you look at the periodic table, it depends on the table, but some of them have Roman numerals, some don't. Hydrogen's always on the left. And then you've got that first column. And then next column over, you've got beryllium and magnesium. And that keeps on going down. And then you have this kind of box in the middle. These are transition metals. And then over here, we have boron and aluminum, keeps on going down. Carbon and silicon, keeps on going down. Nitrogen and phosphorus, keeps on going down. oxygen and sulfur. The column keeps going down. We'll do fluorine and chlorine, keeps on going down. And then helium, neon, and argon in that last column. So this is my simplified periodic table. To find the number of valence electrons, it's pretty simple. Just say 1, start at that far left. Anything in this first column will have 1 valence electron, assuming it's neutral. The second column, it'd be 2. And then basically skip that entire middle section. You see that big indent in the middle there? And then go to boron. This one has 3, 4, 5, 6, 7, and 8. So that's a really simple way of determining the number of valence electrons. So for neutral atoms, all you need to do is find that number. And these are referred to as main group numbers. Equals the number of valence electrons. Okay. We do have to pay attention, though, if we ever run into an atom with a charge. So for charged atoms, you're going to do the following. You'll take the main group number, that's the thing that I had in red on the table, and then you'll subtract the charge that's shown, and this will give you the number of valence electrons. So let's do an example of this, and I'll show you how to do this quickly with charged atoms. Let's think about fluorine that is 1 negative. What's the main group number for fluorine? If we count our rows and go over, we said that that was in 7, so main group number would be 7. And then we subtract the charge, which is what? 1 negative or negative 1. All right, what's 7 minus negative 1? 8. So make sure you do pay attention to math rules. So this one would have 8 valence electrons. All right, does that make sense? So you can use that as a really simple tool. All right. Last but not least, we're going to finish up kind of going back to the periodic table a bit more. And we'll be done with this chapter and get into more interesting stuff next week. And I did want to briefly describe some of the names of these columns. I said it briefly the other day. We saw that video where they threw these into water and they exploded. These are the alkali metals. Oh. These are always group 1 elements, right? So in that first column. And then in the next column, you've got these ones. These are the alkaline earth metals. They're also pretty reactive, but they're now in main group 2. They have 2 valence electrons when they're neutral. These ones down here, we're not going to worry about too much for the time being. These are referred to as transition metals. And then the next block is kind of mixed. You can see we don't have columns of the same type of color. So instead we're going to switch all the way over here. These are group 7. These are referred to as halogens. They're always group 7. And then last but not least, I've got this giant purple column. And these are called noble gases. And we'll talk a lot more about noble gases, but noble gases tend to be very unreactive. They're happy molecules. So these are the main groups that you should kind of remember. Alkali metals are always group 1, first column. Alkaline earth metals are group 2, second column. And then we kind of skip over to the other side. Halogens are group 7, and noble gases are group 8. It is weird, if you look at the periodic table, there's these blocks down below called the lanthanide and actinide series. It's a bit confusing understanding where they go. Yeah? Yeah, try to know the names of the groups that I've just identified. Yep. So the lanthanide and actinide series don't really fit well in the periodic table, and you can see they have asterisks here. And what that basically means is that these two go where those asterisks go. Another way of thinking about it is you can stretch out the periodic table and insert them where those two little asterisks were. So it's actually its own unique block. Does anybody know why we don't show our periodic table this way? It's too long. It doesn't fit on paper well. So this is actually a better way of viewing the periodic table, but it just looks funky. So I did want to show you where those two blocks fit in. They're not separate and removed from the periodic table. They actually fit into that unique section. All right. So let's briefly describe some of the terminology. So group is a vertical column. Those were those numbers that I gave you in red. They have similar reactivities. And they have the same number of valence electrons. That's why they have the same reactivities. This is different than a period. A period on the periodic table is horizontal. And they have different reactivities. And they have an increasing number of protons. As you move right. So try not to flip-flop groups and periods. Primarily we're interested in groups because of their similar reactivity. All right. There's also different types of elements in the periodic table, and they can be classified into a few different groups. Oops. By their physical properties. All right, the first one is pretty simple. It's all of the elements that are metals. Then we have non-metals. And we have metalloids. All right, what's a descriptor we could use to identify or describe a metal? If you had to describe it to somebody that had never seen a metal before, how would you describe it? What's that? It's a solid? Okay. I will say usually, if you've ever played around with mercury, mercury is a liquid metal, so that's kind of the one oddball exception. You can also melt some metals under really high temperature, like in a furnace. So they're solid usually under normal conditions with the exception of mercury. Usually they're shiny. Right? So most metals, if you polish them, have this shininess quality to them. They're also good at conducting. Right? Gas isn't a very good conductor, but metals tend to be good conductors. It's why we use them in wiring. They also conduct heat really well, so this means conducting both in terms of electricity and heat. Another property of a metal is it's malleable. What does it mean if something's malleable? You can bend it or twist it or form it into a new shape, right? If you do that with a non-metal, it'll oftentimes not work, or it will shatter or break or something like that. Metals you can actually form shapes out of. And these typically have a large density. Right? Metals are typically thought of to be pretty heavy, right? Much heavier than a gas when you're comparing densities. All right, nonmetals are not always solid. You can think of gases, right? They're nonmetals. They're quite clearly not solids. They're not usually very dense. And they tend to be poor conductors. Of heat and electricity. There are some exceptions to this. So for example, graphite in your pencil is made up of exclusively carbon. Carbon's a non-metal, but it can actually conduct electricity rather well. So there are exceptions to these rules. And then metalloids are kind of in between. In general, though, it's pretty easy when you look at the periodic table to identify what's going on. So, really simple drawing of the periodic table. I will say hydrogen's kind of the outlier here, but all of these in this section are thought of as metals. The ones that are kind of in between here are metalloids. And then the ones on this far side over here are going to be your nonmetals. This is pretty generic. It won't work 100% of the time, but it's a pretty simple classification for breaking down what type of stuff you're looking at on the periodic table. The metalloids have properties of both sometimes, so it's kind of hard to characterize them in a simple way. Does that make sense? All right, I think that's where we're going to end off today. Next week when we come in, we're going to actually start building molecules and looking at reactivity, but we had to do a lot of this background stuff first.